Hello everybody, I will start my today's another live coding session. So in my today's video, I will solve this question. Find a peak element. A peak element is an element that is strictly greater than its neighbors. A kind of local peak. Now, given a zero index integer array nums, find the peak element and return its index. If the array contains multiple peaks, returns the index to any of the peaks. I see. You may imagine that nums -1 is equal to nums n is equal to negative infinity. In other words, an element is always considered to be strictly greater than the neighbor that is outside of the array. You must write an algorithm that runs in O log n time. Okay. So in this question, I will understand the question first. So in this question, I'm giving an array, integer array. Yeah. Nums, and the output should be the index of the peak element. Okay. So good, I understand. So I have something I'm wondering now. If there's always a peak or not. That's my first thing I'm wondering. Because, for example, if I'm given something like, firstly, my understanding is, for example, in this case, this is a peak, and for this case, I can't find the peak. So I'm wondering, is that? Oh, but I can find here, nums I is not equal to nums I plus 1. So the neighboring two numbers, adjacent two numbers, are always different. So it can't be. So I think that being said, I can always find the answer. Because if two numbers are different, I have two choices. I will go up infinitely, and in the end, this one becomes the peaked element. Or if there is some point that I go down, the number goes down, and I don't know what happens next. But in this case, here, this 3, the number just before going down becomes a peak. Yeah. So I can say there's always a peak. Good. And one more question is length of the nums array. I mean, if the nums array has at least one element or not. And I can say this question is true from this constraint. So I can always find an element. Yeah. Good. So still, I can say there's always a peak. And as the question says, I can return any index, which is a peak. Good. I've understood. So let's think with some examples. So obviously, as I said, the brute force approach is that I will use the, I will iterate each index and check if it is a peak, and if it's true, I will return it. I can already return it. So that's the brute force approach. So it takes O n time. Yeah. And O of 1 space. So I will optimize this. So as I said, it goes up until some point, then maybe then it goes down, or it keeps going up. So I have to I try to find this element. So, and the thing is, I can say is, I have to find any of them. If I can find one of them, it's good. In this case, I have to find this or this or. This or 2, 4, 5, going up, 6 going up, and going down. Yep. So as I said, I'm looking for up-down pair or sorry, going up and down, going up and down, go up and down. And I can find 4 or 5 or 6. Okay. So if I try to find it in log n time, so let's think I have some segment which has a peak, and I have another segment which doesn't have peak. Which doesn't have peak means that it has to go down. Like this. In this case, say if I choose 13, take a look at 13, I will think of the binary search, if I can use the binary search. And if I take a look at 13, I can say, no, I can't say. Maybe there is a peak inside of this, or maybe there is a peak inside of this. Yeah. So what I mean. But I think what I can say is, if I compare these numbers, I'm at here, and I will compare these numbers. If it's going up, I mean, 13 to 14 is going up, in that case, there should be a peak on this side. Yeah. But 13 to 12, when it is going down, I can, maybe there is a peak inside of this, like for example, in this way. But also, I can say there may not be the peak like this. So again, I would say, if it is going up like 13 to 14, there is at least one peak on this side. And obviously, if this is, yeah. So like this, there is a peak, at least one peak in each of left hand side and each also right hand side section. Okay, and if it like this 13 is a peak. I will quickly write it again. So here I said something. Yep. So in this case, I will see this side. So if in this case, this is the one, and in this case, I can this or this. And if it is 10, 30, 15 like this, in that case, peak can be at least here. Maybe there is on the left hand side, but I can just forget it. And in this case, peak is there is at least one peak on the left hand side. Yeah. Good. So I can do the binary search. Okay. So my idea is I use the binary search and I start with 0 and ranks last, and okay, I will just write the condition of the how I will narrow down the scope. If okay, no, sorry. I think this is quite obvious, so I will start the implementation soon. So the time complexity should be now O of n. Space complexity should be O of 1 because I don't use any extra, non-constant base data structure. Good. Okay, so I will start the implementation. And I will compare these three numbers. So in this case, I will return the mid index because now it's a peak. But I have to take care if mid to minus 1 is -1, it goes out of the boundary. So left num I will do this. Yep. So this is, in this way, I could cover this case. So I will think of other cases. Okay, so now I've covered, in line 49, I covered this case, and actually I also covered this case. And in line 52, it is covered in here. Okay, so now I can say I cover those cases here, and it's going down. I mean, the scope is narrowed down. And here I can say, cannot reach here. And maybe it's useful to show low and high in the end. Okay. Oh, no. I'm using low and high. But here I was saying right, left. High should be here. Low should be here. Okay, looks good. So, yeah, let me try run my code. Just confirm. But again, I would quickly say, review my code verbally. So I start the index with low 0, high, the last index, and until there is something in the range, I do take a look at the middle index and check left num and right num. Yep. And yeah, so if left num is smaller than right, middle number is the largest, I will return the middle index because it's a peak element. And otherwise, if left number is larger than middle number, definitely there is a peak in the left hand side, so high should be middle -1. Otherwise, right number is larger than middle number. In that case, there should definitely be a peak in the right hand side. So I narrowed down into the right half. And in the end, I can say definitely there is a number. So if I can't find and go out of the while loop, I return the exception. Good. Okay. So I will take a look at some cases. Let me go with this case first. In this case, I expect index 1 is returned. So this is a test case 1. In test case 2, I will check what happens if going up. Or maybe I'd like to check if it's going down. Yep. So I will check this one first, and maybe I will check the second one or third one. So in this case, low is 0, high is index 3 minus 1 is 2. So I start from here. And currently low is larger than high. So Middle is now 0 plus 2 divided by 2 is 1. So middle is now 1. So left number is now middle minus 1 is 0, so index 0, so it should be 1. And right number should be middle plus 1. So which should be index 2, which is 2. So now middle is 3. No, middle index is 3. Yeah. A bit confusing, but it's okay. So num's middle is 3. So now I can say it's 1, 3, 2. Yep. So in line 56, this is actually true. So I return the index middle. So I return index 1. Good, this is as expected, passed. Okay. So I still haven't covered line 59 to 62. So I somehow would like to see if it's working fine in terms of the code coverage. So I will take a look at this case. In this case, I start with low 0 and high 2. And the same thing happens. And middle is now 2. Sorry, index 1. And left num is 1 and right num is 3. And from here, in line 757 is not true because it's now 1, 2, and 2, 3. 2 is not larger than 3. So I go to line 60. And left num 0, num's middle, which is left num 1, num's middle is now 2. So this is not true in line 60. I go to line 67, and low is middle plus 1. So now low becomes here. Yeah. So now yeah. Okay. And I go back to line 53, and low is equal to high. So now middle is low is 2, sorry. Yeah. Index 2. So so now I can say left num is 2, right num is this one, minus infinity. So now it's num's middle is larger than left num or right num, so I return middle index, which is currently index 2. Good, I passed this case. Okay, I almost covered all the code. I think I haven't covered this one, line 55, latter, latter result in the if state expression, and also which one was it? Line 62, yeah. High is middle minus 1. I'm pretty sure I can cover it in test case 3, but overall, I'm pretty confident in my code. I will submit. Good. Good, accepted. Okay, I will quickly wrap up. So today I solved the question, find peak element. In this question, I'm given an integer array nums, and my task is to find the peak and return the peak index. So yeah, there was a condition that two adjacent numbers in the array are not equal. So that being said, I can definitely find at least one peak. And the approach I used was to use the binary search. So I choose the middle index and compare that middle index with left adjacent number and also with right adjacent number. And if the middle number is the larger than left number or right number, is the peak, obviously. Otherwise, if left number is larger than middle number, I narrow down the scope of the binary search into the, left half, because I can say at least one peak on that side. And or if right number is larger than the current middle number, I narrow down the scope into half into the right adjacent, the right segment, right subarray, because there is at least one peak on the right hand side. So in that way, I could narrow down the scope by half, by half. So it took overlog and time only. Yep. So I could solve this question in that way. Okay, that being said, I finished my today's coding practice. Thank you so much. Bye.